Hey, good day, everyone. This is Andy and Dave from Cubex, and welcome to our webinar today, Automating Kubernetes Resources in Real Time. We're going to show you how we eliminate kills and resource waste with automation. I think it's probably one of the most important topics we can imagine these days because the UI can be pretty and shows all kinds of cool stuff with graphs and charts, but at the end of it, if you've got hundreds or thousands of workloads and you can't fix them and have the environment manage it for you safely, then we have a real problem. So we want to show you how our technology helps you do that automation. Morning, Dave.
Morning, Andy.
I'm going to be your host. Dave is going to do all the hard parts in terms of explaining the technology and showing us a demonstration of this live. I'm just going to go through a few slides up front, just 2 slides. Kubex, if you didn't know, we are AI-driven resource optimization for Kubernetes workloads, for GPU and AI workloads, and for cloud. And our main claim to fame is to help customers cut costs and resource usage, but also improve performance. At the end of it all, it's really all about automating our recommendations safely. One slide in terms of how our technology works. So we analyze workload patterns. So we go through the historical workload patterns. In this case, you'll see in a long example, it could be 30, 60, 90 days worth of history. Raw data for containers, for the nodes and the cloud services those things are running on. And we apply deep policies to basically scientifically determine what is the best setting based on what that thing has done in the past. So we look at this. So we'll go through that deep historical usage patterns. We'll add in replication patterns in terms of how many times has this workload been replicated, because that will tell us exponentially there may be additional waste or additional risk that needs to be factored in. We add in policy, and essentially with policy-based analysis, what does that mean? Essentially means the ability to treat different workloads differently. So you're not going to treat, say, a production critical application with the same kind of conservatism as you would with, say, something like a test dev type of workload. So the ability to, more than one size fits all, it's specific directed policy. From there, we come up with our recommendations to right size the pods themselves, as well as the nodes and the GPUs. So technology will go through that and make specific recommendations on how to fix the waste and fix the risk. And then key to all that, and the topic of this webinar today is the automation capability. So how does our technology take that and enable you to automate that in place in real time? And then also on top of this is built with agentic technology in the front, natural language query that allows you to interrogate our UI without learning every single screen, and also AI capabilities, which is also driving the automation in the back end. Now I'm going to turn this over to Dave to actually run through this live and show you how it works.
Fantastic. Thanks very much, Andy. So what we're going to do today is we're going to do a deep dive on automation, and we're going to go beneath the covers and talk a little bit about and demonstrate how we can deploy our automation controller within your environment and use that to, in real time, optimize resources within a Kubernetes cluster. To show that, what we're going to do first is we're just going to take a quick stop in the UI, just have a look at the before picture of our Kubernetes cluster that we'll be analyzing. What you can see here is a visual representation of the current optimization state of the cluster that we're going to be working on today. What you can see in this visual and in these charts are, in red, we've got the risks. So the containers within our environment that are undersized from a resourcing perspective, you can see we've got CPU requests and limits and memory requests and limits represented here. Anything in red represents containers that are at risk because they're undersized. When we talk about risk and undersizing for CPUs, the risk is that you have the potential of CPU throttling taking place because you haven't requested enough CPU capacity for these workloads. And then from a memory perspective, the risk is out of memory kills because you haven't requested enough guaranteed resources, and therefore there's the possibility that you'll experience out of memory kills. Everything that you see in these charts that is yellow, this represents a distribution of the containers within our environment that are oversized. So we've requested too much capacity, and that results in waste. It means that we're going to scale out too many nodes within our cluster. Those nodes are going to be sitting partially idle, and therefore you have capacity that you're paying for, you're incurring cost for, but you're not actually utilizing it all. So it's very important to optimize these and to eliminate the red, which is risk, the yellow, which is waste, And just to show you a little bit more about the analysis behind this, keep in mind that each one of these, you can see here that we've got 15 containers where we've got a significant amount of over requesting of CPUs. If you click on this, and we won't do this in great detail today, but if you click on it, you'll notice that we've got a set of all of our containers within our cluster beneath that graph. This is actually showing them by the ones that are most oversized. And for each one of these containers, we've set recommendations on what the ideal size would be. So you can see what the current CPU requests are as well as the recommended. So the key thing to keep in mind here is that for each one of the containers within our cluster, we've looked at the current utilization and we've run it through an ML algorithm and determined what is the best sizing for this container. And now what we're going to do is walk through how you actually automate that. Now, in your environments, automating this is relatively simple. Within the UI, you can go to the individual cluster, or you can drill down to individual namespaces or workloads. You can just right-click on this and click on Enable Automation, at which point the automation controller will take over and will automatically mitigate these risks and the waste within your environment. But today's demo, what we're going to focus on is we're going to go a little bit beneath the covers. We're going to look at how do we actually deploy the automation components and how can we observe automation taking place in real time. So in order to do that, what I'm going to do is bring up a command line, and we're going to switch back and forth through a few different windows as we firstly have a look at the current state of our environment. So how much capacity are we currently using from a node's perspective? What's their utilization? Can we notice any patterns as far as waste within the environment? Run a quick command here. This is going to show us a list of the nodes within our current cluster. The command I just ran is a simple little PowerShell script that really just parses the outlook of kubectl and just shows things in a more graphical visual representation. So really what you're looking at here is ultimately just kubectl output. We've just prettied it up a little bit. What you can see here is we've got 3 nodes within our cluster. You can see that all of them show relatively high CPU reservation. So requests within our cluster are very high for CPU, which is something that we saw in our example when we were looking at the UI. But there's a huge gap between the actual CPU requests and reservations and the CPU utilization. So there's this huge gap. That's a common situation we see in a lot of customer environments where if you ask an application owner or someone who's in DevOps, how much CPU do you need? Often they're going to say they need a lot of CPU, when in reality, the actual utilization might be relatively low. This is a pretty common scenario we see in a lot of customer environments where we've got a lot of requests for resources, but we're not actually using them. So our automation can help resolve those problems. But to do that, let's actually walk through deploying our automation controller and observing right sizing happening in real time. What we're going to do at this point is we're simply going to run a simple Helm command to install the automation controller within our cluster. And that should only take a few minutes to execute. So what it's now doing is we've deployed the resources that we need for automation into our cluster. They're still standing up at this point. So there are still some services that are being started, some deployments that are kicking off. And what we will do at this point is we're going to switch to another window and watch some of our cluster resources in real time. And we're going to specifically watch one particular namespace. So at this point, we're just looking at the fact that there's a number of pods deployed within this namespace, and we can see what the current CPU requests, CPU limits, and whatnot are. Now, we're just using this as an example so that when we start automating and when we start applying automatic settings and right-sizing our environment, we'll be able to observe it taking place. The key thing to take away from what we're looking at here is keep in mind that all of these CPU requests are the same, all of the memory requests are the same, and we're not setting limits anywhere. Once automation starts, you're going to see that these numbers start changing. So really, that's the purpose of this screen, is just so that we can observe when automation kicks off. Another thing we're going to do as well is we're going to switch over here and we're just going to start watching the logs of our automation controller. Those are going to start outputting to the screen as the automation controller does work. And you'll notice that there are a few things. So already it's started up, it's showing us some messages. This is all really completely normal operations. So you're going to see that at the moment, we're not right-sizing containers yet. And the reason is because we haven't downloaded our recommendations from our SaaS instance yet. So this is all perfectly normal. We're going to let this run for a few minutes, and then we're going to come back and we're going to be able to observe automations taking place. While we wait for this, let's switch back to a really quick PowerPoint, and I'll just show you a little bit about the architecture of our automation solution. Looking at it from an architectural perspective, on the right-hand side, you've got your Kubex instance running in the cloud. This is a SaaS-based solution, and it's ingested historical data on your Kubernetes workloads. Again, run that through an ML algorithm to determine what ideal sizings are for your containers. And now it's got those ready to be actioned. Everything on the left-hand side represents things happening within your Kubernetes cluster. We've got the Kubex namespace. We've got three components that make up our automation controller, and explain what those three components do in this process in a moment. Then you have some workloads here in the middle that are operating, and those are the workloads that we're going to right size. And lastly, you've got node infrastructure that supports the running workloads within our cluster. Let's look in more detail at how this workflow operates. First of all, we start with passing our sizing recommendations from our Kubex instance into our data store, which exists within your Kubernetes cluster. So we're going to store those locally so that if, for example, if there was any network connectivity issues, you want to have a local copy of all of those recommendations, at which point we're going to start the automation process. Now, an important thing to keep in mind, as far as the automation process is concerned, is this is defined in a YAML file that includes a couple of important things. And I'll just point out what we've highlighted here in a couple of green boxes here that are important to the operation of the automation. First of all, we have what's called automation scopes. So this is where we say, what objects are we going to automatically set? That can be set at the namespace level, it can be set at the cluster level, it could be individual workloads. So there's a ton of flexibility to say, what are we going to automate? It's not just a switch where you have to automate everything. You're completely in control throughout this. And then the second box shows the fact that we have what are called automation policies. So for each one of these scopes, you can have a corresponding policy where you can say things like, am I going to do downsizing? Am I going to do downsizing of perhaps CPU but not memory? There's a ton of flexibility here. Do I want to do in-place resizing, which is a new feature supported in Kubernetes 1.33? If I can't resize a container in place, do I want to evict it? Yes or no? So there's a ton of capability here that allows you to really fine-tune what's being automated and exactly what settings are being automated and how. Moving forward, at this point, we now have the automation director that is used to right-size containers that are already running. So for containers that are already running and that can be modified or resized in place, we start by resizing all of those. So we'll just illustrate that with a quick little animation here that just shows those workloads shrinking, becoming more efficient through in-place resizing. Now we'll also have some workloads that are already running, but they can't be resized in place. The most common cause of this is, for example, due to them having to cross a QoS, quality of service boundary. So there are some workloads that can't be in place resized. If you've enabled pod eviction, then those containers will be evicted in a controlled fashion, respecting things like pod disruption budgets. And the way we illustrate this is we're just going to show that we have some pods that are going to be evicted, restarted, and when they're restarted, they pass through the mutating webhook and are resized to their most efficient sizing automatically. Lastly, we have perhaps new pods or restarted pods that you restart manually. These ones go directly to mutating webhook. So when they're created, from the moment they're created, they're already optimally sized. So that's how we handle all the different permutations of standing up workloads and automatically right-sizing them. Based on that, once you have fully optimized your workloads, they're going to be more efficient. They're not going to require as many resources. And as a result, you're going to end up having a node scale down event within your cluster, whether you're using Carpenter, whether you're using Cluster Autoscaler. You're not going to need as much infrastructure. So you're going to scale in those resources and not be paying for as much node capacity moving forward. So you'll have performance improvements as well as cost savings.
And one quick question just popped in, and it's probably a timely place to interrupt you. Is just customers running GKE Autopilot. Typically, the cost is incurred at the node level, but not with GKE Autopilot. So how does this help them if that's the case and they're running like a serverless technology?
It's a great question. In fact, the connection is much more direct with GKE Autopilot. So with GKE Autopilot, you are not paying for the node infrastructure. But what you are paying for is the requests on those containers. So actually, as soon as you right size those containers, that's going to instantly impact your costs. You're going to achieve instant savings because you're paying for fewer requests, fewer resources. So it still works the same. You achieve the same savings with GKE Autopilot. It's just very direct.
Cool. Gotcha. Okay, that's great. Thank you.
Okay. Now let's check in on the deployment and automation of our environment. Great news. We can see here, if you'll recall, we just had a couple columns here that were filled in before. Now you can see that, again, this is just a sample namespace, but it's just showing that we've now got memory requests and memory limits set for all of these. They're all unique. That shows that we have automated the right sizing of these containers within minutes of having deployed the automation controller within our environment. Let's now switch over, and I just wanted to show you as well the logs. We're going to scroll up a little bit because we've actually gone through a couple iterations. We've already fully right-sized some of these containers, but I just wanted to show you an example of where we're actually seeing the right sizing take place. Just a few examples. So here's an example of individual containers where in the logs, we can see that there's been a resizing event and it was an in-place resizing event. So I have that enabled in my automation scope, and you can see a number of these. So there's a bunch of different containers that we resized. All of those were in-place resizings. You can actually observe that in this screen here as well. You'll notice that the age of all of these pods is measured in a number of hours. So there were no restarts. Our workloads continued running. They were resized, fully optimized without ever having any service interruptions. That just quickly shows you the effect of the automation and how quickly and easily you can go from not having any automation in place, deploying the automation controller, and having the right sizing of your containers, thus reducing risk and reducing waste with minimal effort. Now let's just have a quick look at the end result of all that. We showed you a moment ago what the current state of the environment was. We got 3 nodes that are fairly heavily requested. Let's have another look at this. So what we can see now is after we've right-sized everything, we've actually been able to downscale to a single node. Now that node does have high CPU reservations, but again, this is a single node now that we're operating as opposed to 3 nodes. So we've reduced our node capacity by about 66%. Significant savings can be achieved. You'll also notice that CPU utilization is much higher at this point. That's a good thing. You want your nodes to be as utilized as possible. So what we have here is we have increased CPU utilization, but we also have capacity left over for bursting as well. So this is illustrating to us that we're able to significantly reduce costs simply by automating and right-sizing our environment. Let's have a quick look now at the same cluster. So this is the before. Key takeaway here, lots of risk, lots of oversizing. If we now look at a snapshot of this exact same cluster after it's been fully optimized, you see these just right bars where everything is sized as it should be. Everything is consolidated into just right. There's still a couple of workloads that may need to be right-sized. That's normal. You're going to have usage patterns that change over time. You're going to have some containers that perhaps can't be preempted, and therefore it's perfectly normal. But what you were able to do was, with minimal effort, You were able to eliminate a huge amount of risk. You were able to reduce the possibility of out of memory kills, of CPU throttling, and also significantly downsize the overall cost of your environment. So huge improvements here. Just want to mention a couple of automation controller features that maybe aren't quite as easy to demonstrate. So again, I did mention the fact that we have very flexible policy-driven automation. So you are always in control of both what's being automated and what types of settings. So do you want to enable downsizing in prod? Maybe you only want to do that in dev. Tons of flexibility here. We also have tons of safety checks in place. This is particularly relevant to when you're doing pod evictions. We do that in a very controlled manner. We respect limit ranges. We make sure that before we terminate a pod, that we ensure that there's a node that can accept the resized pod. That's a limitation that tools like VPA don't have. We're HPA friendly, we respect quotas. Really, we're talking about the safest automation solution. And lastly, you notice that we report everything to logs so that you can have an audit trail. And in addition, that's also reported up to your SaaS instance. So you can also view that automation history within the product itself. In summary, what have we looked at today? We're able to see that the Kubex automation controller right sizes Kubernetes pods in real time, reducing risk, reducing waste. There's tons of flexibility about our automation scope. You're always in control of what is automated and how, and we have the safest automation solution on the market. The end result being you're able to optimize workloads, and by doing so, you're able to trigger node consolidations. We saw 66% savings in this example. Typically, we see up to 70% cost savings through automation with Kubex. That's really what we're able to observe today. Andy, I'll check with you. Were there any other additional questions before I hand it back to you?
There was one other question. I think it was subtly answered by you, Dave, in the demonstration. And we hear this a lot as well from customers around Carpenter, saying, I'm using Carpenter today to optimize my nodes. And how does this thing add value? And I think it's a little bit subtle in terms of we saw nodes get scaled down in this environment. Now Carpenter could be handling that, but it's what Kubex is doing in the background that enables that to happen.
Yeah, absolutely. Kubex complements Carpenter. So Carpenter is a very good product, very good node autoscaler. However, if your workloads aren't optimized, that's where you see these situations here where you're requesting tons of resources, but you're not utilizing them. In this kind of a situation, Carpenter will gladly scale out more nodes for you, throwing hardware at the problem, when really the underlying problem is your workloads are requesting way too many resources, but it's far more than they're actually utilizing. So Carpenter and Kubex work together. Carpenter scales out nodes that are appropriate for the pending workloads. Kubex makes sure that those running nodes are as utilized as possible and are running efficiently. So really, they very much work hand in hand.
We have a trial available for anyone who would like to kick the tires on our technology. It's a 60-day trial. It's the full enterprise version of our software, no limits on number of users or number of environments you want to analyze. And it will work for your Kubernetes environment as well as your cloud, your IaaS estate. And more importantly, on a day-by-day basis is the GPU optimization as well. So that's the subject for a completely different webinar, but we're seeing huge overspend in those environments. So give it a try. Just go to our website, click the button, and you can get started. It only takes a few minutes to get the data collection happening. In terms of resources, we've got a couple of great guides. The one that's available today is the one that's around just Kubernetes efficiency, balancing performance and risk. You can download that ebook today. There's another one you can sign up for and pre-register that will be available mid-February. That is an engineer's guide to AI infrastructure efficiency. So how do you optimize those GPUs? Some really cool tips and tricks in there. So I think two great resources available for you today. That is the end of the presentation here today. Thank you everyone for joining us. Keep an eye on our events page for the next one, and we look forward to seeing you next time. All the best. Take care.
Thank you.